Welcome everybody to our October 13th, Friday the 13th edition of our Akka.net community stand-up. We're keeping it nice and spooky for the month of October here. So my name's Aaron Standard, and I'm joined by Gregorius Sodharmo, who works with me here on the Pettibridge team. We've got a very exciting show and tell presentation today from Jim Alexander and Vagif at the NRK organization. They're going to talk about running their media distribution engine, which is built on top of Akka.net and F#. But before we dive into that, we kind of want to cover some of the current and future releases of Akka.net that we've worked on since our last stand-up. So I think the big thing we'll touch on is Akka.net 1.53. So we shipped this towards the end of August. And so I guess actually maybe we did cover this during our September presentation. Whatever, I'll go over it again real quick. The biggest thing that we did here is one of our directives that we put out into the wild after Akka.net 1.5 became stable is that we're going to gradually try to move some of our core infrastructure off of some of our homegrown abstractions we built inside Akka.net into some of the newer APIs that have been introduced to .NET Core and now .NET 5 and 6 and 7 and 8 over time. One of them is that we replaced the hash wheel timer with the periodic timer. This should greatly reduce the total amount of idle CPU that Akka.net uses behind the scenes. We are going to release an Akka.net 1.5.14 that fixes a minor bug with the hash wheel timer. It can kind of block the actor system from exiting for a few seconds. It's just a little design oversight with the way that's built. So we're going to go ahead and I think, Gregorius, you've actually already fixed that, haven't you?
Yep.
So
we just need to do another release, and that's it.
Yeah, we need to do another release. There's a couple of other little bug fixes that we want to try to sneak into there for dealing with some other minor issues. Zenova's reported a couple of bugs around memory leaks in Akka streams and other issues like that. We want to try to get some of that investigated, get all that bundled into release and ship that. You should probably expect that to be out before the end of October. So we'll probably get that done. Let's see. And I guess from this point forward, we should probably go ahead and introduce our show and tell guests who are going to go ahead and be running that part of our presentation today. So I'm going to go ahead and add Jim Alexander and Vagif on stage. All right, fellas, thank you for joining us today on our Akka.net community stand-up. I know you've been long-time Akka.net contributors and users going back, gosh, it's got to be 6 years or so at least. Does that sound about right?
Yes, it's about right.
Yeah, about right. So I remember we were
7 years from 2016.
Yeah, sounds right. Because I remember, that's right. We met in person at your offices, I think in February 2017. So quite a long time. Yeah, in Oslo. Yeah, quite a long time ago. So without any further ado, I would love to have the NRK team go ahead and talk us through their media distribution engine they've built using Akka.net and F#. So why don't you two go ahead and take it from here?
Yeah, thank you. So our presentation today is of our media distribution engine at the NRK using Akka.net and F#. Just first, let us quickly introduce ourselves.
Yeah, I'm Vagif. I work with F#. Earlier worked quite a lot with C#, and as Aaron mentioned, I've been involved in our distribution engine, which is codename Odd Job since 2016.
And I'm Jim Alexander, and I work for NRK, and I saw Vagif had his Twitter handle on there. I'm not as hip as him, but you can add me on maybe like Letterboxd or Last.fm, something like that. So quickly, I want to talk about NRK to put you into the context that we are working in. I don't think a lot of you maybe have heard of us or know what we do. So NRK is the public broadcaster of Norway. And if you wonder what the public broadcaster is, just find your country on this map, and that is your public broadcaster. So public broadcaster is a company that gets funding from the government to do stuff like radio and TV programming. And NRK started in the 1920s, I think. There were some local radio stations around that time, but NRK tried to tie them all up, give them some common infrastructure, and after the 30s, we got the public funding, and from that point on, NRK was the only allowed radio station in Norway, I think. Then after a while, we also got TV, and legally, NRK was the only allowed TV station until about the 90s when TV2 came. In the today's world, this translates to two of our applications, NRK Radio and NRK TV. We also have a lot of other products, nrk.no, which is our news site, which you can read news articles. We have Yr, which is a weather service. I've heard it's actually been used quite a lot around the world, so maybe you've used Yr. And we have NRK Super, which is our platform targeted towards kids. They have kids TV shows, kids radio shows, and other content aimed at towards kids. So the ones we are mainly going to look at are these four, and these are some screenshots from the websites. And what is common for all of these websites is this, a media player. So as you can see, for radio, we have the audio player down here, and for TV, we have this video player. So we are creating this sort of common component that is used across a lot of our services at NRK. So this is kind of our internal, very far out overview of how the process looks. We have all of these are kind of teams at NRK that specialize in one part of the process. So it all starts with program planning. This is for radio and TV. They plan out also for stuff that runs on linear TV channels. Every program that is scheduled in there, and they ingest the raw media in this raw media management tool. So this is where all the raw content files live. Then further down the pipeline, they order transcoding of those files, so they generate the different qualities that we want for streaming. So you may be used to from YouTube, you can go to the little gear icon and choose the quality you want. We have to generate all of those qualities from the raw media content. Then it goes along to the media distribution engine, and we have to upload all of these files to the content origin. So they are responsible for segmenting all the files in 5 second chunks so that your browser can load in the chunks that they want, streaming them while you're watching. After we have uploaded the files to the content origin, we publish them to our public API. We publish here the routes to the CDNs, and the clients can ask the public API, hey, I want to get the streaming links for this and this show, and they get the URLs towards the CDNs. And if anyone from NRK are watching this is like very simplified, I know, and I found some diagrams internally of how this maybe actually looks. So this is a kind of overview of our subtitle process, and this is a diagram I found that was made some years ago, and I think you can be glad I didn't go into detail on these. So Vagif, maybe you want to do a head dive into the media distribution engine.
Yes, thank you for the introduction, and let's move on to, let's focus on the actual media distribution engine. So if we look at like basic tasks, about what it does, is that it all starts with some sort of commands which are sent using queues. Then based on these commands are enriched using metadata, and so distribution engine then creates so-called media set commands. Media set, it can be news clip, it can be a radio program, TV program, like anything that can be consumed by the end user. Then, of course, it needs to access media archives to get the actual media files, which can be audio, video, subtitles, upload them to origins, and finally send events, again using queues. So if we look at our architecture at large, so what you will see, like on the right-hand side with a brown background, it's an Akka cluster. So we started with non-clustered version, but soon we realized that we wanted to be scalable, available. So using Akka cluster is the way to go. And of course, we have some persistent actors. I'll talk more about decisions which we made to make some actors persistent, and some of the errors which we made on our way. And this is our distribution engine on a busy day. It actually happened during one of the weekends. So they started publishing clips from some event. So there was like thousands of clips gathered. And then I thought, oh, that's actually much more busy than we typically have it. So let's take a video so we can use it in some presentation. Because what you see on the left-hand side, it's events. We use Akka distributed pub/sub, and you see this every tile represents media set. It's in this particular case, it's a news clip, and you have two rows. You have different origins, and every icon, which is either green or gray or blue, well, it's and every icon is actually an actor, file upload actor. So actually, what is happening now? It's a very intensive file upload, and it's been for the whole weekend actually, and it's been going very well. So no human interaction was needed. So it's kind of gives a great overview of what the system is doing, and of course, it's just a not tiny, but maybe it's the most significant part of our actors, but not all actors, because we have a lot of other actors that prepare these file actors to do their jobs, and then in the end we send notification. So it's other set of actors involved. So our technical stack, it consists of course Akka.NET. We use F# as our main programming language, and in the end we'll have some code examples. We use Ackling as not sort of official Akka.NET API, but Ackling, which is it's based on same principles, but we think it has better persistence API, and also it supports things like cluster sharding. So it's kind of step forward from the standard Akka.NET F# API implementation. Then we have different durable queues like RabbitMQ, Azure Service Bus, and of course we have various types of databases, both SQL and NoSQL databases. So why did we choose actor model? Actually, the first generation of media distribution engine was written in C# using classic OP principles, using like solid principles. It was actually working very well, was quite stable. But when we needed to add quite significant changes to that, we realized that we can actually build more simple code. I think personally, and I think probably the team also shares this view, that the proper modeling of real-world process interactions with actor model, it works very well using actors to build real-world processes. Also, in the first generation, we had a lot of thread synchronization, and with actors you will have very simple threading model. Also, actors are very good. Actors with state, you can easily build them as state machines. And of course, in our case, we're using clusters, so it solves our needs for scalability, performance, and with actors you get resilience. So if you choose your supervision strategy correctly, then it helps you a lot. And I think already on the second year of our development, we went for cluster, which helps us to scale out the system to have fallback. So it's very easy to deploy. We have multiple nodes, which we deploy quite often. In our test environments, we deploy many times a day. In production, also often several times during the day. So it really helps having cluster. So I want to go through some of the lessons from implementing the actor model, because I think that probably most of you who watch this presentation are already familiar with the actor model and akka. And we made some mistakes, and it's often interesting to learn from mistakes, especially from other mistakes done by others. So I will start from the first lesson. It's that we don't use traditional OP to model interaction. And the first version of slide said don't use OP to model interactions, and that was wrong way to say it, because as somebody said that actually actor model is OP done right, because if we quote like Alan Kay on objects, what he thought about he actually coined the OP term, and he was thinking about OP as messaging, local retention, protection, hiding of state process. So actually, if you think what Alan Kay meant about OP, it's pretty much actors sending messages to each other. And a sign that you're trying to adopt this traditional OP, like derived from C++ and similar languages like C# and Java, is that, and in the first year, probably, or first couple of years of our use of actor model, we had a lot of managers and dispatches, because we need to upload a file, but file shouldn't be uploading itself. We need a file manager. So we have the actor file manager that are uploading a file. So often you have like user account manager, shopping cart manager, and soon we came to realization that actually every resource is a good candidate for being an actor. So your entities are your actors. Our actors are very inexpensive, so we shouldn't be hesitating to turn them into actors. So that was probably the sort of the biggest structural change in how we build actors, when we realized that we should like put we should make our entities acting as actors. So each file is an actor now. You saw in this dashboard, written by the way also in F#, that like every file is has an actor behind. So second level is like plan your persistence right. And I think those of you who read this big blue Eric Evans book about domain-driven design probably have learned that he recommends to put persistence in aggregate root, and that's a good practice actually, that your aggregate root, like actor responsible for aggregate root, becomes persistent actor, and that was our mistake, and I guess my personal mistake, that we had persistence scattered around, and that that gave us some trouble. So we have Mediaset controller, which is a control of TV program entity or radio entity, and then I have multiple files. And in the first generation, we had persistence on aggregate root level, and each file was also persistent actor. It was really hard to build a state out of this. So, and if you take a TV program, which typically has like 5 or 6 files and then 2 origins, so we already have like 12 files. And if this program has multiple parts. It can be like 24, 36 files. Also, you have subtitles. So it can be quickly like 40, 50 entity IDs, like persistence IDs. And it was really hard to manage, and it was not efficient. And it was a lot of like communication. So Access was trying to get hold of their states. So in second generation persistence, we put persistence all on aggregate roots. Of course, files, all events, they go through file actors. File, of course, owns its events, and it's the first source of its state. But then it forwards the events to the Mediaset controller, which puts it in event journal. So there might be slight asynchronity between like when the state is written. So you need to think about like eventual consistency in that case. But in our case, it's relatively easy to solve this eventual consistency things. And also our system is generally idempotent, so it doesn't hurt actually to upload a file twice. In some systems, like financial systems, there can be different requirements. So that brings me to the third lesson, which is actually related to this second lesson. Don't expose actor state directly from the persistent layer. That was kind of being naive in the first version, that we, even though we all knew quite well about CQRS and respected CQRS, but really didn't think about it when implemented collecting state in our web API. So every time somebody asked about state of our actors, like we went through the cluster sharding and tried to find where the actor resides and ask its state and brought it back. And of course, that really contradict the CQRS principles, because you have event journal which is optimized for writing, and you should have your cache, like state cache, optimized for reading. So this is how it works now. It's relatively simple change, but it also took some time to realize that we did it wrong in the first place. So that was quite important thing, is that leave actor state relation to actors themselves. So in the beginning, again, having mindset of managers and dispatchers, we had something like some state monitor that was telling actors what to do. So and we still have actually Mediaset monitor that goes through programs, TV programs, radio programs, finding out what is left and trying to push them. Please do your job. But in the late incarnation of actors which we build, we don't do that. Like actor itself get the message, wake up, find out what you need to do, and do your duties. I will talk more about the so-called desired state which we implemented. So this is second generation Mediaset recovery. So we have reminders which remind actors to wake up, and they don't remind actors about particular command. They usually remind actors about just figure out themselves what they need to do. And it's been working very well and simplified quite a lot of things. So and that's leads us to the like fifth lesson, is that like we because actors represent reactive software. So and of course with reactive software, some of your entities are sleeping most of the time, so they need to be pushed to do their jobs. So we use as I said, reminders to wake them up and remind them about their duties. And currently we're using Akka Quartz Actor. So it's also an actor, and it's an actor maintained by Petabridge, which works flawlessly with our needs. Then sixth lesson which we learned is that we should not ask actors. We should rather tell them what to do. And that's pretty common mistake of those who start working with Akka, I guess, because you see there are two method calls. You have tell, you have ask, and you say, oh, that's we have the best of both worlds. We can send single messages, and also we can have messages that require response. So like we can have these interactions where we need immediate response, and it's really bad practice to do it. First of all, ask is very, very slow. Also, it's the way it's implemented. It requires some intermediate actor to be created, and also it breaks these principles of sequential message processing. There is a very good article written by former member of actor team Bartosz Sipitkovsky, where he describes why ask is very slow, and he comes with some suggestions what you should be using instead of using ask. And his suggestion is to use so-called aggregation pattern. So actors are state machines, and then if you need to get response about certain things, then you don't need to bring your actor in the model state, so it's blocked and waiting. It can just get into different states, and in that state it can still process some other messages, and those messages which it can't process, it just simply stashes, and it stashes them when it receives a response which it's awaiting. So there are very few exceptions in our code base where we use ask, and there are some special reasons for that, but mainly it's just this aggregation pattern. So we don't use ask. Also, begin with non-cluster system. So we have akka.net running in a cluster, and but that's a different sort of dimension, and this is different levels of complexity. So if you plan to, if you're starting with akka.net, I would suggest to start with non-cluster system, because it's a change of mindset. Like in our case, it was. So I think you will gain a lot of experience by having cluster in mind. For example, to plan your aggregate routes right, to plan your persistent rights, what will be your future cluster sharding, but like don't start with cluster from the day one. Then yeah, so this is a snapshot of our cluster in one of the environments. It's a test environment, and the snapshot was done using PBM, this Petabridge monitoring tool, which shows nodes, and you see that they note they are in different roles. So lesson 8 is once you start using cluster, then like with persistence, you should really think about like domain-driven design principles when you choose how you shard your cluster, what you use for what entities goes as cluster sharding. So in our case, it's media set, which is a base, which is foundation for cluster sharding. So which means that we must plan our messages that we send in our system, that when we receive message from RabbitMQ or service bus, message should contain something that can be extracted as entity ID, so we can then send it to proper shard. So we used mostly cluster sharding. We used some clustered pool routers. So this is an example of cluster sharding. We have message queue, message parser. We extract an entity ID, and then it's sent to the shard, which will be responsible for its processing. And of course, if we redeploy the system while it's working, then the shards will be rebalanced. So yeah, we use cluster pool routers, not as much as cluster shard, but they also have place in our system. And we have a few cluster singletons, but we try to avoid them. And for the same reasons, like developers usually avoid traditional singletons, like when they don't speak about clusters, because singleton is you have like something which exists only in single instance. For example, if you have partitioning problem, and then you have like partition dice where singletons are running, then you can be in problems. So if you can, it's not always possible. Try to spread your activities on different nodes without using singleton. So we have example of one of our singletons which we still have. It's a health check. We have like health check singleton, which we thought that we would because it's doing a lot of checks. Then okay, it will be just one actor that is doing all this. Then it'll be running as a singleton. But today, and maybe we'll come back to that, I would say that we will be better off. We will just place multiple health checkers around the cluster, not being dependent on just a single actor to run. Don't rush to heal split brains. When we started this cluster, we thought that we must use split brain resolver because, of course, you will experience partitioning, and then you have to be prepared. So, and we rushed on choosing split brain strategy. And in our case, it was not really that easy because our nodes, they're not like symmetrical. Our nodes playing different roles. So whatever strategy we use, like we are at risk of losing some roles that that will not be in that partition that survives. And then when we were figuring out the best strategy, actually at that time, it was about like 5 years ago, there was a great article written by Peterbridge team. I guess Aaron contributed quite a lot to that article, that in many cases you don't really need to apply any particular strategy, because in our case we have cluster, it's all running on like local machines, and for the reasons of like we have huge files locally. So we have because of traffic, because of we want to run most of our cluster nodes locally. And so if you have some network speed, then most likely within fraction of a second the system will be fine. Also, our system is idempotent, so we have also we are also better off if the split exists for some time, unlike some other systems where actually the split brain can lead to catastrophic failures, like financial system, if you start like sending financial transactions multiple times. Finally, I'd like to say something about message handling guarantee, because with actor systems, you have at most one message delivery. So how can you build a reliable system using sort of unreliable messaging? If you look back and look again at our architecture, this our architecture at large, we have durable queues only at entrance of our system, also when we send messages to those who listening to our notification. But internally, we don't use any durable queues. So how do we manage that? Our message configuration, this is example of how we configure rabbit queues. They have a main queue. In this case, it's subtitles in production. And then we have error queue. We have rejected queue where invalid messages comes. We have retries. So if there is an error, we put message into retry queue, and then it goes in error queue after some time, and then eventually it will be rejected. And in the beginning, when we started working with Akku, we thought that okay, our queues, our rabbit queues, will be as transaction guards. So we actually didn't acknowledge message until it was finally handled. And you see, it's not really a good idea when you need to upload 5 GB file. You see, so if you think about how real world functions, I mean, do you really need to keep a message unacknowledged while you're working on a quite expensive and long running transaction about it. So also it makes a quite complicated like intermediate processing. You have a chain of actors, and then each actor in the middle can it can't acknowledge message, but it can only knock the message. So, and it's only final actor should acknowledge it. So it makes the whole thing quite complex. So actor should remember, okay, if it's about its place in this transaction. So can I act, or should only knock? It was really hard to maintain such code. And at that time, we were implementing so-called return address pattern, because messages that had to be enclosed in envelopes with this acknowledgement information, so which should be sent all the way. So we had it was not sufficient just to send message payload. We had to also to send ACK ID. So there was we saw that there was quite a lot of drawbacks with and added complexity with handling messages that way. But I think probably the most disadvantage was if you think how real world works, it doesn't work like that. You shouldn't make postman wait until you're done with the letter, until you write response, or until you read the letter. So, and I think the more we work with actor system, the more we get convinced that we should think about how real world processes work, because very often they work in a very efficient way, and we should learn like from the nature. So then we had an intermediate version. We started using at least once delivery using ACK extensions. I think ACK recently updated at least a guaranteed delivery, and it's better now. But in that version which we used, it was really hard to use. Also, you needed to the protocol was quite complicated. Messages had to include delivery ID, and each delivery requires confirmation from recipient. So it was also really complicated programming experience, and it didn't feel right actually to use that instead of maybe just using grab it and queue. But then we thought that approach, and then we thought, okay, we should probably think about a radically different approach. So current version, it uses what we do, we try to fulfill desired state. So there is an article by Mark DeGraw, Nobody Needs Reliable Messaging, where he talks about that if reliability is important on the business level, it should be done on the business level. And another quote on the same thing, that in a system that cannot count and distribute transactions, the management of uncertainty must be implemented in the business logic. It's from Pat Halland. And finally, again, to recall what happens in the business, in the real world. So, work happens with a sequence of related messages over time to perform cooperative work, and this is how it was done centuries ago, and it's how it's done today. So we rethought the things, and so what we ended up with current version, when we receive incoming request, we evaluate the desired state of our aggregate route, like where we want to come. And this desired state also includes information about expected outgoing message, about expected notifications. It's a called outbox pattern. Then we persist the desired state and acknowledge the message, and we proceed with the request execution. So to summarize in brief, like evaluate desired state, evaluate current state, and then remaining work is current state minus desired state. So it's pure math. And then message is act, and then actor just needs to be periodically reminded if it's not in, if it has some work to do. If it doesn't have work to do, it does need to have a reminder. So while it has some work to do, it just needs to be awakened from some time to time, compute what it needs to be done, and do this work. So the concept of a desired state, actually, it's not ours. It goes to several systems. One of them, of course, it's well known for Kubernetes. Like you describe the state of the object that will run the containers, and then Kubernetes is in charge of doing that. And the same you have is PowerShell decides the configuration. So this is how it works in our system. So we serialize desired state of our media sets of TV programs, radio programs, news clips, and acknowledge all messages which we received, and then actors started their work, and they are not finished until the work is done. Of course, important assumption is idempotency. And if your system is not idempotent, and then if you are at risk of bad consequences of rerunning certain interaction multiple times, then it's yeah, you have to rethink this. So this example of our desired state. So you have a desired state which consists of a couple of files. You have a partner number, quality ID, file name. So this is something that needs to be uploaded. And then this is a current state. This is one of our origins. It's a former origin, Akamai. And here it's files which are uploaded. So if there are some deep, then there are some remaining work. So when we publish media set, we generate desired state, and then we look at current state, and here's the work. You see, it's just a plain diff. Of course, as I mentioned before, actors are reactive, so we schedule repeating reminders, and so actors get their job done. And our reminders, they don't have any command. They just it's just plain reminder to actor for do his job. Yeah, so main lesson learned from multi-actor behavior actually is consider using patterns established in real-world collaborations. So the real world is solid, and if we try to sort of learn from real world, then our system will be robust. So, and with that, I will give back word to Jim Alexander, who will guide us through a few examples of the source code written in F#.
Yeah, so I was thinking we could go through some actual actors and show you how they are implemented with F# and Acklin. So the first one I was going to show you is an actor that is responsible for just taking commands, upload this file to S3 bucket. And the way we are set up in this context is we send in this actor these, think of them as like constructor parameters, things that we need for this actor to live. So we need a S3 client, some file system info. This is interface to check our local directory for files, if it exists, how big the file is. We need some path mappings for Linux and Windows kind of stuff. And then we have this one, ingester ID. This is because we scale up to 20 actors that do this kind of upload. So this was based on some experience we had earlier with an earlier origin that we used. If we try to upload more than 20 files in parallel, they would kneel down and they didn't want to take it. So we have become quite cautious when uploading a lot of stuff in parallel. At least with we have some direct fiber lines going to some data centers, and yeah, it can get too much with these actors. And if you try to scale it up, some systems go down. So every ingester has this ID, and then we also have some instrumentation in Influx. So this is how you would start an actor. It's just a function, like everything in F#. The answer is it's just a function. So you send in the props and the mailbox, and as you can see here, if you're not familiar with the F# syntax, this is how you define a function. You say let and the name of the function and your parameters. And then you just write your code, and the last line is what's returned. So if I mouse over here, this is a function log actor state. It takes a string and it returns a unit, so it returns nothing. So the same thing here, we define the S3 actor, 2 parameters, and it returns an effect that you might be used to. So if we look down here, we define a lot of functions, and then we call this one idle. So we can take a look at what's inside here. So the way we like to structure our things is we have kind of these functions on top. You can think of them as kind of private functions. And then we structure our actors as finite state machines. So here we start in the idle state, and this is an actor. It takes these S3 commands, and we can take a look at what that is. We can upload a file, we can upload some text, we can move a file, we can update some text, delete a file, or delete some files. And what we do is we set up some a priority queue, an empty priority queue, and then we start executing this message that we got. So what we do is we handle the command. So this is in an async context because it might take a long time to upload this large file. And this is some quite nice syntax. You can await this is an async, so we can await it. And then when we are done, we return this completion status completed. And this method here it just sends a async message to the actor itself when the async is completed. And then we go to this awaiting completion state. So in this awaiting completion state, we can get either a completion status, which would be this completed that we send to ourselves, or we can get more S3 commands. So while we are waiting for one file to be uploaded, it can take some minutes maybe if the file is large, we can get more commands in. So this touches on what Vagif went on about earlier. If we have some long-running task, we just take the message and we stash it. In this case, we use a priority queue because some programs are more equal than others. So we want to handle them first. So we add them to this queue. And then when we get this completion status completed, we just pop out the next message on the queue and we go back to the execute state. And didn't mean to do that. And I think this is a quite nice way to work. You build up these kind of states that your actor can be in, and in this the different states you can handle different types of messages, and it makes it a lot easier to think about. I'm in just this context now. What do I want to handle and what do I want to do? So I was also thinking we could look at a much larger example. I won't go into like super detail, and maybe Vagif wants to jump in too if he has any comments. But it's this one, the media set controller. So this is the large actor that is responsible of keeping track of the current state and the desired state of every single program that we have across our services. So a single program can have a lot of different video or audio files, and it can have subtitle files. And this actor needs to keep track of all of the ones that we want to publish. So here you can see we have a lot of this, I call them private functions. But kind of the state machine is still pretty simple, just 5 different states. We have the init state. This is where we do our persistence. So when the actor starts up, we want to do some persistence recovery. And when it's done doing that, we go to the media set initialized state. And here we can start receiving some messages. Let's look here into maybe the operating state. So this big state actor, it can receive these media set shard messages. We can take a look at that maybe. So you might want to like publish this media set, and you get like this block of just files and subtitles. Just publish this, or you can publish a single file. You can set the geo restriction of a program. If some programs are just available inside Norway, some are just available at NRK, some are available in the entire world. You may want to clear a media set, maybe if a program runs out of rights. And it's, you can just mention right now, it's also a big, it's a very nice part of F# with this discriminated unions. You just define all of the different cases, all of the different messages that your actor wants to handle. And you get a lot of type safety from F#. There's not a lot to it actually. It's bigger, yes, but it's really easy. Yeah.
And it has everything. One of the reasons we're showing it because it's persistent. It uses cluster sharding, so it's sort of the most important factor of our system. But it's as you can see that it's quite easily readable code, and yeah, you get easily the overview of what it's doing.
Yeah.
Yeah, I was going to say this looks very well organized in terms of being able to handle all the different layers that go into your processing. And I'm not a super adept F# user myself. I'm a big fan of it, would love to use it, but even I can follow what you're doing here quite easily. So I think this is very well organized.
Yeah, at least the other smaller actor, it can get quite a lot sometimes, but I guess that's all projects. I think we're nearing the end of our presentation at least, so maybe we have some questions maybe, or...
Yeah, absolutely. Let me bring Gregorius back too. Well, thank you very much for the super thorough presentation, guys. I really appreciate it. And Vagif, I thought the 10 lessons you laid out around using Akka.net, that by itself would, I think, make for a very interesting series of, let's say, blog posts or presentations on how you kind of evolved your architecture over the time. That's kind of one of the benefits of, I guess, working with technology for a fairly long period of time, is you get more adept at understanding what are more natural and error-free ways of expressing things. In particular, some ones that stood out to me, I think using persistence for aggregate roots makes a lot of sense, where the idea being that if you have a graph of sub-entities that all are closely related to each other, you might be tempted to go ahead and spin them off onto their own actors initially. But as you discovered, that can result in increasing the amount of synchronization, work, state validation, persistence traffic by like 1 to 2 orders of magnitude potentially, versus having that all self-contained inside one actor. That essentially increasing the size of your bounded context might be a better idea sometimes, right? Yeah. So that made perfect sense to me. And the one thing I wanted to have you expand on a little bit is how you solved your reliable delivery problem with queues. Did you basically break up your RabbitMQ sort of architecture where there were smaller queues between different sets of entity actors, where you kind of disintermediated it rather than it being one big end-to-end processing? You had a bunch of different stages that were all separated by queues.
Yeah, actually, I skipped from the presentation some of the slides which were telling like more in depth, like different stages of that. So we started with rabbit and queues like at the entrance of the system, and then we were not acknowledging it until we were done. And because that was a not really good way of doing it, particularly for example with rabbit and queues, we have time to leave, and that was some reasonable time. Like we have message have time to leave, like let's say an hour. And we had very long file, and it takes more than an hour to upload it. And then then the message actually dies in Rabbit while we're waiting until file is uploaded, and then it's brought back, but file so it starts again, and so on. So then we had Rabbit in queues at the intermediate stages of the system. So it was like Rabbit, and then which receives commands for the whole media set. Then we generate smaller messages, like message for each file. And then so a single message turns into 5 or maybe 10 if you have 2 origins messages. And so we have each file has its own queue. And then by that, we sort of reduced potential retries to only those files which fail. But again, file can be long, and then it didn't feel right to, like, we have akka, which is messaging system, and then why should we like insert this durable queues in between actors? And then we really wanted to solve it in a better way. And also we were not happy also into bringing all this acknowledgement ID through the cluster, so we acknowledge these rabbit messages. And then so we tried next stage was to try guaranteed delivery using akka at least one delivery, and that we were not happy with the programming, most of his programming experience. It was really it didn't feel like intuitive or lightweight. You can say that with at least one delivery, it doesn't have to be sort of lightweight, but we felt that sort of it could be we could do something better than that. And then we eventually went to this desired set principle, that we just record what we want the outcome of the whole business transaction, and then just actor goes back and evaluates its state. Okay, here's my desired state, here's my current state. Okay, maybe I have some work to do. Yes, this is a diff. I'll do some work and then I will fall asleep. So this is how it works now.
Makes sense. And that's reply to sender model with RabbitMQ I've seen before in other code bases that have similar types of, let's say, like staged event-driven architectures where there's multiple phases an operation has to go through, and they don't want to have big long queues waiting in front of everything. I've seen that before in systems like sports betting, for instance. I've seen that.
Mhm.
So that's definitely kind of a nice, natural, robust pattern. I also agree that Akka persistence, the at least once delivery actor, I think the design of it absolutely sucks, which is one of the reasons why we added Akka delivery to Akka.NET 1.57, which I think is a little bit more robust. It's heavier duty and it handles the durable sort of queuing stuff a bit better, but it still might not be as intuitive as just simply doing what you did and having some separate RabbitMQ layers in between actors. So I agree with that. I also thought that your assertion about start with Akka.NET first locally in process and then move to clustering later is a really good way to introduce Akka.NET to an organization. Um, Akka.NET by itself, from a syntax standpoint, is not hard. It's very, very simple in the grand scheme of things. And the semantics of working with actors locally, in terms of how message passing works and everything, is very simple locally too, because you don't have a lot of those, let's say, network and distributed systems programming problems, such as message loss being a good example of that. I thought that's really good advice. And that's one of the big advantages of Akka.NET, is that you can start with it at a fairly, like, let's say, in process sort of scope, and then gradually move your way towards clustering. I think that's very sound advice, particularly for companies that are looking to, let's say, do what you did, transform a piece of, let's say, legacy software that's working that's working but needs to grow and evolve. I think that's another good place to kind of start the transition there. Clustering is indeed very powerful and very useful, but it comes with its own learning curve that is totally distinct from the actor model, in my opinion.
Yeah. Yeah.
I thought that was good advice. So Jim Alexander and Vagif, do you have any other? Actually, well, quick question, Gregorius, do you have anything to ask?
No, not really. The whole concept is really neat.
Yeah, absolutely. I mean, you guys gave us kind of a 30,000-foot view of NRK systems, but you can tell that there's some fairly complex stuff running under the covers there.
Hmm.
And that it's very impressive that you've maintained and built this system over all these years and evolved it and speak so confidently about it now. We really, really appreciate that. So, for some parting thoughts here, do you have any other advice or wisdom you want to share with the greater Akadonic community before we adjourn? Maybe
Uh,
things that weren't on the PowerPoint.
mm. Maybe let me ask a question, because we went through some lessons which we learned. Is there any particular lessons which you sort of disagree with, or you think it's not that important, or there may be it may be mislead somebody, because you don't need to agree with what they say.
No, no. Um, the domain-driven design facets around persistence and aggregate roots, it very much depends on what type of entity you're working with, I think. In your case, aggregates are a naturally occurring phenomena in your system because even something that looks like a single entity, TV program, is itself actually composed of a whole graph of subentities underneath it. But recognizing that distinction between all those subentities doesn't actually add any value in the actor context is a really important design decision. So if you're going into, let's say, modeling something with the actor model with like a DDD, Eric Evans sort of purist perspective, you can end up with this sort of explosion of different entity and actor types that ends up complicating your design without really adding anything in return. So I would say that is very much it depends on what domain you're working in. And I think based off what you've shown here, NRK's domain naturally can be expressed heavily as aggregates. Other domains, to give you a good example, we're leveraging the same pattern you came up with around don't share actor state directly to the non-actor part of your systems. Use CQRS and projections and optimize for read models separately from your Akada persistence-based write model. That's what we're doing for like the new version of SDK bin we're working on, for instance, where we have an event journal all around, let's say, new versions of packages being published, API keys being activated and deactivated, all that sort of thing. 100% of our actual web API is leveraging some read-only entity framework models that are being synthesized using projections from that data behind the scenes there. And the reason being is that we want to keep our write model fairly, let's say, flexible in terms of what new events and everything we might incorporate down the road. And we want the ability to resynthesize all of our read models anytime we want. That was another piece of advice I think would be worth expanding on. The sort of CQRS. I'd say the kind of like an there's like two really big understated superpowers of Akka.net. One of them is Akka Streams. I think people who really get it can't imagine programming without it once they start getting into the guts of it. The other one is how strong Akka.persistence is at doing CQRS across any arbitrary database. There's not a lot of other tools that can do that. So those are two areas where I feel like the Akka.net literature and training courses and really the body of work that's out there from third-party users as well would richly serve the rest of the community. So I think that's a really interesting insight on its own right, so even independent from the other 9 lessons that you had.
Mhm.
Yeah. But other than that, I think most of the lessons that you mentioned there are really important. I really love the graph you had on the performance around ask versus tell. Whenever I see performance comparisons between, let's say, Akka.net and Orleans, they're always using Ask for Akka.net because Orleans uses the same sort of RPC model that's basically request response fundamentally. And it's like, okay, well, that's like not the way idiomatically Akka.net is designed to work optimally, you know? So it's kind of like the fingers being put on the scale there. Now, don't get me wrong, it's still really important to support request response, but that's not sort of our first class citizen when it comes to design
Exactly.
in the system, right? So I always feel like that's kind of an unfair ding against us. And then when you have, let's say, a benchmark that does incorporate it, then the Orleans people whine about it. That, oh well, you're not prioritizing Akada, you're not prioritizing how consistently and how blah 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 and all the other, let's say, things that Orleans prioritizes as its first class design model. Whereas it's kind of just important to recognize that there's different, let's say, there's different sort of idioms that each framework kind of emphasizes for a lot of reasons that are ultimately pretty arbitrary in the grand scheme of it. But in Akka.net, it's the idea that you should have everything should be asynchronous and non-blocking, and that's why you have tell, right?
Yeah.
So I thought it's really illustrative, kind of showing like you're shaving off 2 orders of magnitude of performance when you start using ask, and probably more than that if every single actor is asking each other and everyone's awaiting, and as a result you have a lot of blocking flow control everywhere. I should also point out that in addition to being rough from a performance standpoint, you're much more likely to run into things like deadlocks when you have those types of designs. Whereas if everyone's using ask and behavior switching, that never, oh, sorry, tell plus behavior switching, then that never happens in that system. So,
Yes, we had plenty of timeouts in our logs while we were using ask.
yeah, I can imagine, and that's all symptomatic of someone awaiting on something else. That's awaiting on something else. That's etc. So I thought this was a very rich set of nuanced points, and I thought the way your code was organized too was very helpful. And I hope it provides some inspiration from our F sharp community, who are constantly at the forefront of doing all sorts of innovative things on top of Akka.net. But it's really nice to have an F sharp clustering sample. So thank you very much for doing that. We really appreciate you and the team at NRK. I'll reach out to both of you and make sure I send you guys some Akka.net t-shirts. If you don't, or I know you've probably got some Vagif from years ago, but you'll get a new one.
Okay.
So I'll go ahead and reach out to you guys and send them. We always send them to our community stand-up speakers. And in case anyone else is interested in presenting in the future, you can always go ahead and hit me up on Discord. I'm Aaron on the web on there, and I would be hapful. I was about to say happy and helpful at the same time. There, hapful. I would be glad to go ahead and accept your submission, and you can get a Knock It On a t-shirt for you and your team members as well. All right. Well, thank you very much, everybody. Have a great rest of your weekend, and thanks again to the NRK team. We really appreciate you.
Thank you.
Thank you.
Take care.
Bye.